All right. What is the first thing we always do in a proof? We mark the given, right? So it says given BEC is congruent to CFD. Now I still realize that some of you are slipping through the cracks and still do not know how to identify angles. Yeah, I'm serious. Some of you are like, I have no idea where this angle is. Remember, what is the letter that determines where the angle actually is?
Middle.
The middle, okay. And then what are the surrounding letters here?
It's supposed to make like that.
Right. So we know that E is the center, and B and C have to form like the brackets that hug the angle, right? So angle BEC is centered where? BEC is centered at E. Is it this angle?
No.
Is it this angle?
No.
No, because B and C, the other two parts of the angle, are not the other two sides here, and they're not the other two sides here, but they are here. So BEC is this angle right here. BEC. Remember, the definition of an angle is created by two vectors. So B and C are the other ends of our vector. Where is CFD? It's at F, and the other two ends of the angle, the other two ends of our vectors are C and D. So CFD is here. So those two are congruent, and then EB is congruent to FD, and angle EBC is congruent to FDC. So EBC is this bottom, and FDC is right there. Now, ignoring the large triangle and also the middle triangle, what do those two side triangles make you think of?
Isosceles.
Side angle is.
Right. We had a whole unit on triangles that looked just like this with parts marked congruent, right? And we had been asked in that unit to identify how we know triangles are congruent. Well, do we have enough parts here to say that these two triangles are congruent? Yes, and they're congruent by ASA. Angle, side angle. Angle, side angle. How does this help us? If the triangles are congruent to each other, what does that mean?
Every angle inside of each one is congruent.
Yes. Once we know two triangles are congruent, then we know everything is congruent in those two triangles. How does that help us?
Sides are congruent.
Right. So if we know these two triangles are congruent by ASA, we can then say that this side, let me make that thicker, that this side is congruent to this side. How? What is the reason? Not by the ASA. That's how we know that triangles are congruent. By CPCTC. Right? That's how we know that these two parts are congruent, because once we know two triangles are congruent, then all of the corresponding parts on one triangle are congruent to all of the corresponding parts on the other triangle. Basically, CPCTC. Do we now know this is isosceles? Yes, how? By the definition of isosceles triangles.
I'm still confused.
It's all right.
Can you write down the proofs?
Oh, don't worry. I'm just walking us through the proof before we're writing it down, of course. So now, let's go ahead and write it down. We have our statements and reasons. First is always the given, which you all are going to write down, but I am not. What did we do next after we marked the parts congruent that are given? We realized that these two triangles are congruent. So triangle BEC is congruent by triangle DFC. And how do we know? By the ASA postulate. Oops, what was it? Then what?
Then you said that there's EPCTC.
Then we said EC is congruent to FC, how? By CPCTC. Corresponding parts of congruent triangles are congruent.
Is this on the test too?
Wait, is the long one?
Like, this proof is similar to the one on the test. The long one is not. Now, what did we then state? That triangle EFC is isosceles.
Is there like a symbol for isosceles?
No.
Would you like this?
Yes.
Would you say the converse?
So technically, and I'm not going to mark off for this, but technically, what does the definition of isosceles triangle state?
That's two sides.
If a triangle is isosceles, then the triangle has two congruent sides, right? So technically, we want the converse of that. So you would say converse of isosceles triangles. Am I going to mark off for that? No, it's okay. But technically, yes, it'd be converse of isosceles triangle. Oh no, definition. What am I doing? Definition of isosceles triangles. And we're done. That's what we wanted to prove.
On the test, if you don't mark it up, you say it out.
I should.
You're not.
We shall see. You should always assume I'm going to mark off if you don't mark the triangles. One, because you're making your life harder if you're just trying to visualize something, right? That's just making your life harder versus actually seeing it on paper. Any more questions on this proof?
I'm gonna do the proof last.
I have a question
Yes.
on question 8.
Yes. Well, all right. Any more questions on this proof? All right.